Okay, so the next important thing is the background. We've talked about what nuclear chemistry is. Now we need to put a background to what we're about to be studying. And what we're about to be studying is nuclear chemistry. And we're going to be studying things that are to do with the inside of your atom. Now, when you talk about the inside of your atom, there are things that you must know. First of all is the notation. And then we'll talk about the particles and how they change the notation. So we need to know how they represent things. And the numbers you must be familiar with. You must know what each number communicates to you. So there are some terms and there are some things that you have to know which make it easy. Now let's try to go through those things, okay? That's the reason why we are doing this. We're going to be talking about the atomic number, mass number, the atomic mass, just so that you know these terms, and when you see these numbers, you're dealing with them, they all make sense to you. So let's go through it. What is this? Let's go line by line. I'm going to stick to the notes, and I'll be explaining from there. The first one says all atoms of an element are identical in atomic number, but not all of them have the same mass number. Okay, basically, what we are dealing with is atoms, and we're going to be talking about the inside of the nucleus, right? Now, when we deal with that, there are certain numbers of things that are in the nucleus. Okay, these numbers are of things that are in the nucleus that we'll be dealing with. And there's a certain number called atomic number. The reason why they call it atomic number is it is distinct. Each atom has its own atomic number. So every element, let's say each atom of an element, let's not say that each atom, but let's say each element has its own atomic number. So say hydrogen, all hydrogen atoms have the same atomic number. Helium, all helium atoms will have the same atomic number. Same if we look at iron, all the atoms of iron will have the same atomic number. So atomic number is a way that you can know which element you are dealing with. Atomic number, very important, very nice. We'll call it atomic number. You know that all the atoms of that element will have the same atomic number, no matter what. If your atomic number changes, you are going to become a different element. You can't remain being the same element having a different atomic number, okay? But not all have the same mass number. We've said all hydrogen atoms have the same atomic number. So if we see an atomic number of 1, we know it is hydrogen. No matter what, right? We don't have to think twice. We know what it is. Now, there is another number called mass number. Mass number, not all hydrogen atoms will have the same mass number. They will have the same atomic number, but the mass number can change. And what is that? Let's see the definitions, right? Here there's something important we talk about, which is isotopes. And that is a word that is related to what we've just said. Before we've even defined them, you should know that these things that will have the same atomic number, which means they are atoms of the same element, but having different mass numbers, will then be referred to as isotopes. So they will be isotopes of hydrogen. They are all hydrogens, but they have different mass numbers. So we call them isotopes. So isotopes are atoms of the same element, but these atoms will have different nucleon numbers or mass numbers, but they will have the same atomic number. Of course, they will have the same atomic number because they are of the same element, but they will have different mass numbers, which we can also call nucleon numbers, the things that are inside the nucleus. Let's see what atomic number and mass number are, these two. Atomic number will be called Z. You say, oh, atomic number starts with an A, so shouldn't it be called A and then mass number Z? No. Atomic number, though it starts with an A, is called Z. Then mass number is A. So atomic number just tells you how many protons. Remember, we said these two numbers are numbers of things inside the nucleus. There will be numbers of things, and these things will be inside the nucleus. So when we say atomic number, we are talking about the protons only inside the nucleus. Then when we say mass number, it is now the number of protons plus neutrons in the nucleus. But something now becomes nice. When we say atomic number, is the number of protons in the nucleus of an atom. Because what we know is that whatever the atom is, if it is an atom of hydrogen, it will have the same number of protons. So atomic number will be for all the atoms of that guy. But mass number is when you will add protons and neutrons. They are both in the nucleus, right? So now we are combining them and we'll get a number called mass number. And that number is going to be for a specific isotope. It's not for all atoms of a guy. So we are saying when you are asked for mass number, you say it's the sum of the protons and neutrons in the atom of an isotope, or in the nucleus of an isotope, rather. Let's say that in the nucleus of a specific isotope. What is an isotope? It is an atom of hydrogen, but it will have a different number to another atom of hydrogen, right? So we say these two atoms are referred to as isotopes. All of them are hydrogen atoms, but they are different in mass numbers, so we'll call them isotopes. You know isotopes, we talked about them. You can practice until you are very familiar. So A, when you see the symbol, when you talk about this symbol A, it'll be protons plus neutrons. And then we have the number of neutrons, which we'll call N, capital N, number of neutrons. This will be A, which is mass number, minus Z, which is atomic number. So mass number minus atomic number will give you the number of neutrons, because mass number has protons and neutrons. Atomic number has protons. So if you say protons and neutrons minus protons, you remain with neutrons, which is N. Right? Oh, we'll put it somewhere as we keep doing questions and other things. I'll be bringing you back to this. Now, one more thing is this called atomic mass. Atomic mass is the one which you're going to see on the periodic table. Mass number is not there on the periodic table. Okay? Atomic number is there, but mass number will not be there. They will say it is there, but it's not. What is there is the atomic mass. This is going to be the average mass of all isotopes. You know why? Because mass number is a whole number, because you are just adding number of protons and neutrons, so you can't get. But now when you deal with atomic mass, it is going to be in units called atomic mass units. And atomic mass, you say to me, what is the difference between atomic mass and mass number? Here it is. Atomic mass is still, you are still adding, right? But you're still combining the protons and neutrons. But now you will be combining the masses of all the isotopes and you get their mean. But it is called weighted mean or weighted average because you consider how much of that isotope do we have. So let's give you an example. Let me give you an example. Say you have chlorine. Chlorine, there is chlorine 35 and there is chlorine 37, right? These two are different. There is chlorine 35 and there is chlorine 37. Both of them are chlorines, but they have different mass numbers. They are isotopes. Yeah? They are chlorines, which mean that if you look at the atomic number, it's still 17. But their mass number, look, one is 35, the other one is 37. So very different, right? Now, when we deal with these two chlorines, when we want to find, let's say you have been told, I'm not so sure, you can check online. This could be, say, 76% of chlorine is chlorine 35. Is 76, which means that this becomes 24%. So if you now want to get, this is the mass number. Mass number is for an isotope. We said it. For a specific isotope. Then here's another mass number. It is for the isotope. So it's a mass number. Now, when you want to see the one you see on the periodic table is a decimal number, it is the atomic mass. So what you would then do is you say, oh, it's 76%. So you would say 76% is 76 over 100 times chlorine 35. Then you add 24%, which is 24 over 100, of chlorine 37. Then you get your average, your atomic mass. So here I would say 0.76 times 35. I would get 26.6. Then I'm going to say, of course, I'm going to divide by 2 because there'll be 2 of them, right? I'll divide by 2. Then because it's average, you sum, then you divide by 2. So this would be 26.6 plus the other one would be, I'll say 0.24 times 37, chlorine 37. You'd get 8.88. Oh, so no division by 2. 26 plus, I'll say plus 26.6. Here I'll get 35.48. I'm sorry. So it's like there is no division because this is the one which you would then see in the periodic table. This is we've calculated here is called relative abundance, right? Relative abundance, which is telling you how much, 76%. Then here you have again the relative abundance. So you are going to multiply relative abundance times the mass, then you just sum them up. Okay, now I'm remembering. Yes, there's no division. So you just sum them up and then you'd get your 35.48. This would be the atomic mass that you'd see. This 76% is wrong. The one you may see in the periodic table is slightly different, but they use this concept. They always check how much of chlorine 35 do we have, how much of chlorine 37, then they'll find the average. So atomic mass is the weighted average mass of all the isotopes of an element. So it's the average mass of all the different isotopes will be the atomic mass. Then mass number is the number of protons and neutrons in the isotope, in a particular isotope or in a specific. Then this atomic number is just the number of protons. We can say in an isotope, but remember that all isotopes will have the same atomic number if they are of the same kind, because they will be of the same element. Remember, they will have the same atomic number because the number of protons is the same for every single atom of a person. All the isotopes, remember, isotopes are the different versions of the atoms of that guy. But because it is all hydrogen, they will have different mass numbers, but they will not have different atomic numbers. Their atomic numbers will be the same. Okay? Now, the last thing I want you to know is then, what is the nuclear notation that you see? So you would see some nuclear notation and it would be like this. Here is the top number. Now, what I want you to know is you would see it like this. As we say, it says as you go down. If you read going down, this is the bigger number, which would be your mass number rather. Sorry. This would be your mass number. And if it is in the periodic table, it is your relative atomic mass. So it is relative or relative atomic mass, right? Relative atomic mass. But you will not deal with the relative atomic mass for these isotopes. You'll be having the mass number. And then Z is the atomic number. Now, there's something which I'll say as we are going towards the end, is that we've said that the mass number is not there in the periodic table. What is there in the periodic table is the average of all isotopes. But in nuclear chemistry, we'll be looking at one isotope only. We are not taking it as all the guys. So we'll be looking. So if you get something like uranium-235, okay? Uranium-235. It could be saying 235, then I think it says 92, yeah. This is an isotope. If they tell you it decays, whatever, or they tell you that anything decays to give you uranium or whatever, please, you never get this number from the periodic table. This number is not there in the periodic table. If you go and check in the periodic table, you won't get uranium. You won't get 235 on uranium. You won't. It'll be whatever number it is. So that is because this is not atomic mass. This is the mass number, which is the mass of an isotope. Only this isotope called uranium-235. There's another one called uranium-237, which would be probably the one you see in the periodic table because it might be much more in quantity than than 235, because remember, we consider how much you are, your abundance. Your abundance. This was 76, this was 24. So that is why 76 is more part, the 35, the chlorine 35. That's why if you see the mean, it is closer to 35 than to 37, because 37 is not much. Anyway, one thing important is you get this notation. It's called the nuclear notation. They'll give you even as a key on your periodic table. For an atom, listen, for the atoms, remember isotope is a version of an atom, right? For the atom, this will mean mass number and this will mean atomic number. A is mass number, Z is the atomic number. Mass number tells you protons plus neutrons. Atomic number tells you protons. So you can be able to then find whatever you want, right? This one will be protons plus neutrons. Oh my gosh, this is perfect. I love it. I love it. I love it. So now I'm sure you now you can now get this. You can now know this, right? One more thing is, as we're going, I've said this is the atomic number. This is the mass number. But remember, we've said it is for atoms. Okay. Now, when you are going to deal with nuclear reactions, you will not only have atoms. You have atoms, and this is the nuclear notation. In other words, when we say the nuclear notation is, it is telling you the numbers of things that are inside the nucleus of that guy. Mass number is telling you how many protons and neutrons together are there inside that guy that you'll be looking at. And then this tells you how many protons, because those are the numbers we care about. We are in nuclear chemistry. Now, you may then have a particle like alpha particle. It will be like written as 42, or they'll say 42, then give you a helium. Now, if we are now dealing with the particles, I'm going to give you the particles. There are like 7, which you have to know. So I'm going to give you just now in the next video. Those 7 particles, what you should then know is that if it is helium like this, alpha is a helium nucleus. It is no longer an atom. This guy is a particle. It's no longer an atom. So this top is the mass number, true. This would be the mass number. But the bottom number is not only the atomic number. It doesn't only tell you the number of protons. No, it also tells you the charge. So these guys will be charged. These guys will be charged. The nuclear particles, the particles that come from the nucleus, will be charged. They will be charged. Only a neutron. A neutron is the only one, and a gamma ray. But when we're talking about the other particles that come from there, they will be charged. And if you want to know their charge, you just look at the lower number. That is for the particles. I've said it now, and I'll say it again. When we do questions, I'll say it again. And you're going to see how they will become more meaningful, and you understand them better. So anyway, the first thing was, we may have it as an atom. So in other words, if they give me as uranium, this is an atom. I know that this is the mass number on top. Then the bottom number, I know that this is going to be my atomic number, which tells me how many protons this guy has, right? But I know that when I now combine them, when decay is happening, there will be particles called nuclear particles. Those particles, when I even have it written as 42He, this is not helium. This is the helium nucleus. So in other words, there are no electrons, because when you talk about a helium nucleus, the electrons are not included, because an atom will have the nucleus and then electrons outside. But here, this is an alpha particle is a helium nucleus, which means that it will have no electrons. So that means this will also be the charge. There are 2 protons, which means the charge will be 2+. Okay? Either way, that's it. Bye for now. See you in the next video.